So we've been talking about magnetic susceptibility at the micro scale. We've been talking about the susceptibility as something that happens in and around blood vessels and the perivascular tissue, right? And we said if we change the amount of deoxygenated hemoglobin inside intravascularly or extravascularly, that changes the magnetic field. It creates these sort of warpings proportional to the concentration of deoxygenated hemoglobin. And the more warping there is, so the less smooth the field is, the more protons will dephase faster with respect to each other. So this is magnetic susceptibility at the microscopic level. At the macroscopic level, however, this is also very important for us. So this is an image, this is an MRI of a human head. And you can see the brain right here. Now, see, the idea of magnetic susceptibility is the fact that if you take something, a tissue, and you put it inside an MRI machine, the tissue itself magnetizes, and under certain circumstances, for example, hydrogen protons, will themselves create a small magnetic field. So if you think of it, all the protons inside the brain, inside water molecules, all the hydrogen protons inside water molecules inside the brain, they themselves are positively charged, they spin, so they themselves create additional magnetic fields. So if you look at it on this side, on the phase image, which again for us is a shorthand for the strength of the magnetic field, protons inside the brain, the hydrogen protons inside the brain, end up creating small additional magnetic fields on top of the 3 Tesla. So the magnetic field inside the brain is actually a little different than the magnetic field outside the brain. And that's because the certain tissues magnetized and created new magnetic fields. And so anywhere there's a boundary in tissues, there's a risk that if there's a different concentration of tissue that can magnetize, then there will be a difference in magnetic field. And no place in the brain is better to observe this than the sinus. So if you look on the magnitude MR picture on the left, see this hole right here, that's the sinus. And obviously in here, there's a very different concentration of hydrogen protons compared to inside the brain. So this means that here inside the brain, there are protons themselves magnetized, creating additional magnetic field on top of the 3 Tesla. So the magnetic field actually inside the brain is probably a little more than 3 Tesla. 3 Tesla plus whatever individual protons can possibly make in terms of additional magnetic field. Whereas inside the sinus, there's many fewer protons, and so the magnetic field is much closer to 3 Tesla. So this means that inside here, let's just say that here there's no protons. Here it's exactly 3 Tesla. Whereas inside the brain, it's 3 Tesla point something. So at the boundary between the sinus and the brain, there's a transition in magnetic field. It's 3 Tesla in the point just before being inside the brain, and it's a little bit different inside the brain. That in of itself creates a permanent warping around the sinus. And you can see this on the right side. See all this mess right here? Well, that's the sinus and other cavities. And if you see this warping right here, this little white arc, well, that is the difference in magnetic field between the sinus and the brain that causes whatever is inside here to be inside a slightly different magnetic field to whatever is around it. So now there's an area at the bottom of the brain, just above the sinus, that is permanently inside a warping of the magnetic field. So any proton that is inside here will dephase faster compared to protons inside the rest of the brain. And I should say this line right here is actually not meaningful in the sense that the dark side is 0 in phase, so in 360 degrees, and this is 359.99999. Okay, so these two, here it looks like there's a boundary, but it's not a real boundary. But this one here sure is. So now there are certain parts of the brain that are always going to dephase faster with respect to everybody else. And there are two parts of the brain that are susceptible to this. And you need to know it, because if your experiment is about one of those two parts of the brain, you need to ensure that you set your TE accordingly. Let me show you what I mean. So, and by the way, this phenomenon of certain parts of the brain, because they're nearby boundaries with air, dephasing faster than the rest of the brain, is typically referred to as signal dropout. So here's an MRI of the brain, a gradient echo recall sequence. And the image is taken, so radio frequency pulse, you excite the protons, protons go down in the transversal plane, they start dephasing, and at 6.8 milliseconds after you've stopped the radio frequency pulse, you snap a picture, you measure how strong M0 is in the XY plane. Okay? And you can see that we can see all tissues pretty well. In fact, this is almost a proton density image. Now, let's wait a little bit longer. So let's let protons more time to dephase. So obviously the image overall just gets a little bit darker. So this is 10 milliseconds. And now at 20 milliseconds, you can notice that overall the image is getting darker. Of course, right? All tissues are dephasing, have more time to dephase. So the overall MRI signal will be weaker if you wait for too long. But you will notice, and this little arrow is meant to point you to that, see this area here? In fact, there's one right there too. See here, there's an area where protons are dephasing more than the rest of the brain, because this is already dark. And then you can see as you wait longer and longer, 30 milliseconds, 40, 50 milliseconds, you can see that right here and right here, and in fact, there too, there are areas that seem to dephase much faster with respect to the rest of the brain. So they go dark, they go entirely black, much faster than the rest of the brain. And these are areas nearby boundaries with air, between the air-brain boundaries. This hole, in fact, let's look at the one after 50 milliseconds. This hole right here, this black hole that is forming here and that you can see at the front of the brain, it's due to the sinus. Because there's a boundary between brain and sinus, signal drops out much faster than in the rest of the brain. And the same is true in the lower part, in the ventral temporal lobe, so right here, and you can see it also on the other side. And that's because parts of the temporal lobe are just above the ear canal. And there too, there's a pretty prominent brain-air boundary. So anywhere there are these big boundaries, protons that live nearby the boundary are essentially going at a different Larmor frequency than the rest of the protons inside the brain. So those protons will dephase faster with respect to everybody else. Now, as I was saying, this is crucial because if you care about auditory processes, visual processes, stuff that lives nearby the ventral part of the temporal lobes towards the more lateral surface, or if you care about things that are in the above the sinus, if you're doing any social neuroscience, if you're doing other processes that have to do with the medial aspect of prefrontal cortex, then you have to be very careful to set your TE appropriately. Because if you wait too long, let's say that you care about this piece of the brain, if you wait 50 milliseconds to measure how strong M0 is, protons will have entirely dephased and there will be nothing for you to measure. Okay? So it's very important that you know if the part of the brain you care about is susceptible to magnetic susceptibility, more at the macro level, more so than any other part of the brain. Generally, it tends to be two regions: medial ventral prefrontal cortex above the sinus, and ventral temporal cortex above the ear canals. So make sure you know where you're interested in, because else you might risk losing and having no signal in the parts of the brain you care about. And this is because of magnetic susceptibility and therefore the signal dropout that ensues.